Good evening, ladies and gentlemen. I know it's been a while, and I'm going to ask you one. I'm sick, so I apologize. Two, there are going to be duck noises in the background. That's my ducks drive themselves off. Okay. So, you guys, I am trying to, gonna not do the whole thing. I'm actually just going to do evens this evening. One, because I'm sick and I want to go to bed. And two, because I want you guys to get some practice doing it by yourself and not just have kind of a blank answer pad where you guys don't actually have to do some of the work. So, number two. So all of these, what we're going to be doing is we're going to look at these through the Pythagorean theorem, the first set. A squared plus b squared equals c squared. If we flip that around using this symmetric property of equality, we get c squared equals a squared plus b squared. Okay, now we square root both sides. And in doing so, we get rid of that c squared. Okay, so square roots and squares are inverse operations. Okay, so the square root of c squared is c. If you're not sure about that, plug any number you want to in there, run the math, and you'll be great. Okay, now notice that we can't do that on the other side. The square root of a squared plus b squared does not equal a plus b. It's just the square root of a squared plus b squared. So if we did that but what if we wanted to find for something other than c? Let's say we wanted to solve for a. Well, we'd subtract b squared from both sides. We get a squared equals c squared minus b squared. And then we would go ahead and take the square root of both sides. That's going to give us a equals the square root of c squared minus b squared. Now if I wanted to solve for b, I'd subtract a squared, and I'd get b equals c squared minus b squared, or a squared, sorry. So those are your three equations. So on each one of these, what you're going to do, label them a, b, c. Here we're missing b. b is our x. So we're going to use b equals the square root of c squared minus a squared. Then we just plug everything in. 14 squared minus 170, the square root of 170 squared. Now notice here that we're squaring the square root of 170. Okay? And so again, those cancel each other out. So we're going to get x equals the square root of 196 minus 170, or x equals the square root of 26. And that's it. There's nothing doing. You can't simplify that at all. It's 13 times 2. So number 4. Now number 4 here, remember what I told you. That's a, b, and c. Now here we are looking for c, so we're going to use square root of a squared plus b squared. Now this is a perfect example of why the square root of a squared plus b squared doesn't equal a plus b. Here we end up with 16 plus 25, or c equals the square root of 41. Now notice, if we had just gone the square root of a squared plus b squared equals a plus b, we would have ended up with 4 plus 5, or 9. We know the square root of 81 is 9, so clearly here we can go, okay, well that's not right. Now these next ones, I think, are hands down kind of the hardest ones that people face. And these are the special right triangle. So we have our 30, 60, 90 right triangle and our 45, 45, 90 triangle. Now, because of similarity, each one of these has a set ratio, okay? The 30, 60, 90 triangle, that's the one on the left there. The ratio is 1 radical 3, 2, okay? That means the hypotenuse is always twice as long as the short leg, and the long leg is always the short leg times 1, or times the square root of 3. And go through your notes. You should have notes on how that is half of an equilateral triangle. Likewise, if we look over at the right one, we see it's 1, 1 radical 2. That's because it's a 45, 45, 90 triangle. And that means that it's half a square, and that means the two legs, it's an isosceles right triangle, so the two legs are the same. And then the hypotenuse is going to be the square root of 2 times those two legs. So our base ratio times the scale factor equals the final. So here we know that our final is 10 radical 3 over 3. Now that's across from the 30 degrees. That means it's the short leg. Okay? So we have base ratio times our scale factor equals our final length. If we divide both sides by the base ratio, we get the equation that our scale factor is equal to the final length over the base ratio. So here our scale factor is going to be 10 radical 3 over 3 over 1. Anything divided by 1 is just itself, which means that our scale factor is 10 radical 3 over 3. Now your scale factor is always going to be constant. Okay, it's how much bigger or smaller this triangle is than our basic reference triangle. Okay, so here we are going to multiply square root of 3 times 10. Now, it's important to notice, if you have two numbers under the square root and they're multiplying or dividing by each other, you can do that. So, the square root of 3 times the square root of 3 is going to be the square root of 9. Square root of 9 is 3, so we end up with 10 times 3 over 3. 3's cancel out and we get 10. Now, if we have 2 times 10 radical 3 over 3, we just multiply the 2 and the 10 together. We get 20 radical 3 over 3. Don't let the radicals throw you. Then we label them x and y, because that's our job. Next one, this is a 45, 45, 90 triangle, which means it's going to be 1, 1 radical 2 as our base ratio. Now here we're given that the hypotenuse is 2. We remember that our scale factor is equal to the final length over the base ratio, which means that our scale factor equals 2 over the square root of 2. Now here, notice what I did. I multiplied it by the square root of 2 over the square root of 2. Okay, so this is 1, right? But we're doing it that way because when we multiply the square root of 2 times itself, we get 2. And this is what is called rationalizing the denominator. We take that denominator, we multiply it by itself, in this case, in order to get a number that is rational. And that's going to give us 2 radical 2 over 2. Now notice here the 2's cancel out. 2 divided by 2 is 1. So our scale factor is simply the square root of 2. Which makes sense because if we go the square root of 2 times the square root of 2, we get 2. So that checks. And it's an isosceles right triangle. Both sides are the same. X and Y both equal the square root of 2. 10, we have another 1, 1 radical 2. Now here we're again given the hypotenuse, and it's 6 square roots of 2, or 6 times the square root of 2, or 6 radical 2. So our scale factors are final over our base ratio, 6 radical 2 over the square root of 2, which just equals 6, which means that both x and y equal 6, easy peasy. So number 12 on the left side now, totally throwing you guys for a loop. So this is a 30, 60, 90 triangle. Okay? Base ratio, scale factor, final. We know that the base ratio of a 30, 60, 90 is 1 radical 3, 2. And here we know that our radical 5 is the long leg. Now, I know that we're going to be dividing radicals by radicals, and that makes it ugly, but it doesn't make it undoable. Scale factor equals our final radical 5 over our base ratio, radical 3. Now again, we have a radical in the denominator, so we need to clear that. We need to rationalize the denominator. We're going to multiply by 1. Square root of 3 over the square root of 3. Now notice here, everything's underneath radicals, so we can just multiply across. So we get the square root of 15 over 3. So that's going to be our scale factor. I'll put that 2 in later, don't worry about it. So we get our 1 times radical 15 over 3 is radical 15 over 3. 2 times radical 15 over 3 is 2 radical 15 over 3, and we label them for A and B. Now you can either put them into A and B, or you can just have on the actual chart you may just label them A and B. I don't care. 14, we have an isosceles right triangle, which means that our base ratio is 1, 1 radical 2. Our leg is 4 times the square root of 2, so that's going to be our scale factor, because 4 radical 2 divided by 1 is going to be 4 radical 2. Multiply across, and we get 4 radical 2 for the other leg. That's going to be n. And then for the bottom one, we're going to go 4 radical 2 times the square root of 2. That's going to give us 4 times the square root of 4, or 4 times 2, or 8. Excuse me. Next up is 16. Now 16 and 18 are a little bit tougher because we have 2 triangles. Notice that one is a 45, 45, 90. The other is a 30, 60, 90. So we'll start off on 16. We are given part of the isosceles right triangle, and we're asked to find a part of the 30, 60, 90 triangle. Now notice here that the hypotenuse of the isosceles right triangle is the long leg of the 30, 60, 90 triangle. Right there. So we got to start off, got to find out that leg. So we're going to start off with our 1, 1 radical 2. And we know that it's 7 radical 3 is our final for the leg, which means that is our scale factor. Now notice, when we multiply 7 radical 3 times the square root of 2, we get 7 radical 6. So that 7 radical 6, that's going to be that leg. So now we have this 30, 60, 90 triangle where our long leg is 7 radical 6. We're looking for the short leg. So we're going to set up our chart again. We're going to go base ratio times the scale factor. 1 radical 3, 2. And then we have 7 radical 6 as our final leg. So when we set that up, we know our scale factor equals final length divided by base ratio, and we get 7 radical 6 over the square root of 3. Again, because both the radical 6 and the radical 3 are underneath the radical sign, and because we are combining them with division, we go 6 divided by 3 is 2. So 7 radical 2 is our scale factor. Let me just multiply across. We're looking for the short leg. So it's 7 radical 2. The hypotenuse would be 14 radical 2. So x equals 7 radical 2. Again, if you guys get stuck, you don't understand it, go back, rewatch it. Help yourself learn to do 17. We're going to do 18 though. So here... Okay, so computer decided to... update during that, so that was awesome. So here we are, number 18. So we're starting off with that 30, 60, 90 triangle, which has a base ratio of 1 radical 3, 2. Now we see that the short leg is the one we're getting. That's a 5, so that's going to go opposite the 1. So we sit there and we go, okay, what's 5 divided by 1? We get 5, so we know that's our scale factor. 5 times radical 3 is 5 radical 3. 5 times 2 is 10. So notice that that 5 radical 3 is now the leg of the isosceles right triangle. So now we create our second... Hey, Lele. That's my cat, not like just something I say. So here we have a leg. It's an isosceles right triangle. We get 5 radical 3 as our scale factor. Again, we get the scale factor by dividing the final length. Final length is the one we're given. That's the length of the actual triangle. By our base ratio. Our base ratio is what we went over at the very beginning. It's what in this case, the isosceles right triangle always has. The isosceles right triangle will always proportionally be 1, 1 radical 2. The 1 and the 1 make it the isosceles, because 2 sides are the same. And then we go from there. So we multiply across, we get 5 radical 3, and 10, I put 10 radical 3, that's wrong. It's actually 5 radical 6. So let's change that really quickly. Because what we want to do is we want to go square root of 2 times 5 radical 3. We can multiply these two together because they're both underneath the radical. We get 5 radical 6. So that would make our answer there 5 square root of 6. Okay. And, okay, so now finally we're on to something new. Yay! Okay. So, sine, cosine, and tangent are just ratios. That's why if you look at the problem, it says trigonometric ratio. Ratio compares two numbers. Sine compares the opposite to the hypotenuse. See? Sine, opposite, hypotenuse, SOH. Cosine, adjacent, and hypotenuse, CAH. Tangent, opposite side over the adjacent side. So, if we can remember SOHCAHTOA, we remember what each ratio is. Sine, opposite, hypotenuse. Cosine, adjacent, hypotenuse. Tangent, opposite, adjacent. So for 20, we were asked to find the cosine of A. Cosine is adjacent over hypotenuse. Okay, I know I put an O there. I'll change it. Don't worry. There we go. Okay. The adjacent side to the A, that means next to, is the 48. Now, when we're talking about adjacent and opposite, it's important to remember we're talking about the legs that form the 90 degrees, not the hypotenuse. The hypotenuse is the one opposite the 90 degrees. 48 over 50. That's the hypotenuse. 48 over 50 reduces to 24 over 25. And that would be our answer. Now, in all fairness, if you put 48 over 50, I'm probably not going to ding you points. But you guys are at the point in your mathematical careers you really should be reducing fractions as a matter of course, not just because your teacher tells you to. So, tangent of A. Tangent is opposite over adjacent. So the tangent of A opposite over adjacent. Opposite is 24. Adjacent is 32. Both are divisible by 8, and we get 3 over 4. So the tangent of A is 3 over 4. Yay! Moving on. Cosine of Z. Adjacent over hypotenuse. 27 over 45. Divide both by 9. We get 3 over 5. Tangent of A is opposite over adjacent. I did that wrong. It's 15. I put over 25. That's wrong, because 25 there is the hypotenuse. So let's erase all that. This is what you get for doing math when you're sick. 15 over 20. Still both divisible by 5, but here we're going to get 3 over 4. Okay, last one, 28. Cosine of A. That is adjacent over hypotenuse. So that's going to give us the adjacent 12 over 37. 37 is a prime number, so we're done. Okay, so now, here we go. Now for these, you're given all three sides of the triangle, and you're trying to find the value. So I'm going to show you that it doesn't matter which one you use, sine, cosine, or tangent, you're going to get the same answer. Now I'm going to use them intermittently. What I would suggest to use is use the same one every time. Figure out which one you like best. Sine, cosine, tangent. Go with that. Here the sine of x is going to be 9 over 41. Cosine of x is going to be 40 over 41. And the tangent of x is going to be 9 over 40. Now, when we look at this, we now use what are called the inverse operations, or inverse sine, inverse cosine, inverse tangent. Sometimes you'll see them if you have, depending on your calculator, it'll, instead of going sine to the negative 1, which is how it shows up on the graphing calculators in the class, it'll say a sine, and that means arc sine. It means the same thing. So instead of normally I'd hit sine of, let's say, 45, or sine of 30, and that would be 1/2, okay? So instead of hitting here and going sine 30, which then gives me 0.5 as my answer, If I hit arc sine or inverse sine of 0.5, it would give me 30. So the inverse sine is me asking my calculator, going, "Hey calculator," my calculator goes, "What's up?" Because I'm sick. And so my calculator's talking back to me because I'm a little bit delusional from this fever. Okay. So we go arc sine equals of, I'm going, "Okay calculator, what angle has a sine of 9/41? Or, using inverse cosine, what has a cosine of 40/41? Or what has a tangent of 9/40? So if I plug that into a calculator, any one of them, I'm going to get the exact same answer. It's going to say, Mr. Renard, it's 12.6. And then I go, wait, hold on, it's the nearest degree. 12.6 rounds up to 13. So notice if I hit 9/41 and got a number, and then cleared that out, and hit the sine of 13, it's going to be really, really close. Now keep in mind, it's not going to be exact because we are estimating to 13. Even the 12.6 is a bit of an estimation. So the more we estimate, the less precise our answer is going to be. So, the next one, you're fine. The next one, so 32. Here I'm going to use sine. So the sine of x is going to be 16 opposite over 65 hypotenuse. That means the inverse sine, both sides, that cancels out. So I go inverse sine of 16 over 65, and I get x equals 14.2, or x equals 14 degrees. Now here's the thing. At some point I show you kind of how to enter that in on the calculator. I've done that in class, but I'll do it again here. So here I'm going to use tangent. Tangent of x equals 24/7. That's opposite over adjacent. So x is the inverse sine, or inverse tangent, of 24/7. Or x, plugged in on my calculator, is 73.7, rounds up to 74 degrees. Now, so this is what I'm going to do. There are a couple ways to do this. I'm going to hit second tangent, and when I do that on my calculator, this will appear. Tan -1, open parentheses. And then I type in 24 divided by 7. Hit enter, and it's going to give me the answer. The other way I can do it, it'll give me 73.7 something. The other way I can do it is I can hit 24 divided by 7, enter. Then I can hit second tangent and then second dash, okay? Now when I do that, it'll say it'll go tangent -1 like that, and then answer. And then I hit enter again, and it should give me the exact same answer. Okay? So 36, I'm going to use cosine, because why not? That's adjacent, 72, over hypotenuse, 90. So x is going to be the inverse cosine of 72 over 90. So that's the inverse cosine of 72 over 90. So again, let's say I want to go 72 over 90, enter. That's going to give me a number. Then I hit second cosine, second dash, and hit enter. And the number it spits out at me, I'm going to then round up to the nearest degree. It's 36.9, so I round that up to 37 degrees. 38. Sine of x equals 8 over 10. That means x equals the inverse sine of 0.8. So x equals 37 degrees. Now check this out. Notice that it's the same angle. Just kind of flipped around a little bit. So notice that the two triangles are similar. The top one has the exact same size, just times 9. 8 times 9 is 72, 6 times 54 is 9, and 10 times 9 is 90. So it makes sense that we're sitting there and getting the exact same answer. Okay, so now on these ones, it says find the sine of... So we have to find the missing side round to the nearest tenth. Okay, so here, let's look at the triangle. We got 29 degrees, one side, we're looking for another side. So we're given, as I sat there, the opposite side, 17, and the hypotenuse, that's the x. So we have to figure out how we use those to solve for x. So we'd look at our SOHCAHTOA and go, okay, which one has opposite and hypotenuse? Well, sine does. Sine is opposite over hypotenuse. So we go sine of 29 equals opposite x over 17. That's that trigonometric ratio. So now we just need to solve for x. We're going to multiply both sides by 17. And we get 17 sine 29 equals x. So x equals 8.2. And now you can just plug directly into your calculator. If you're using one of the graphing calculators, that's just exactly how it goes. 17 times, you don't even need to hit the times button, you can just hit 17 sine 29, enter, and you're fine. Now if you're using a scientific calculator and that doesn't work for you, you might need to go 17 times 29 sine, but most of you guys are using the graphing calculators. So, number 46, we are given the adjacent and the opposite. So that is tangent. Tangent is opposite over adjacent. So the tangent of 69 is going to be 16 over x. Now this is tricky because the x is in the denominator. So what we're going to do is we're going to multiply both sides by x. So we get x tangent of 69 equals 16. Divide both sides by the tangent of 69. Now I know a lot of you guys kind of go, what? I can't do that. But yes, you can. You can divide by the tangent of 69. That's just, it's a ratio. It's just a number. And the tangent of 69 divided by the tangent of 69 is 1. So they cancel out. So then we have x equaling 16 divided by the tangent of 69. Plug that into your calculator. Again, 16. If you're using the graphing calculator, you just hit 16 divided by tan 69. And you get 6.1. Now, yes, I'm aware I skipped 42, and that's fine. You guys will live. 48, last one. Sine of 58 equals x over 15, because we're dealing with opposite and hypotenuse. Multiply both sides by 15, and we get x equals 15 times the sine of 58, or x equals 12.7. Hopefully this helped out. Gives you a guide on how to do the other half, which you're responsible for. And I'll see you guys tomorrow for the test.